we saw the set R of real numbers, and we saw that we define R basically as the set of all subsets of rational numbers that are cuts. And we had this definition of a cut in the last session. But we also saw that for every real number in R, we can have a representation as an infinite decimal expansion. Okay. Now, actually, I didn't quite prove that, but it's easy to prove, so I'll leave it to you. So you have to prove that every infinite decimal expansion gives you exactly one cut, and every cut gives you exactly one infinite decimal expansion. So you have to show that these two sets are the same, basically. Right. So what I have is that every number, let's call it X, in the set R has an infinite decimal expansion. And remember that when I'm talking about an infinite expansion, I don't consider things like this. I wouldn't use, for example, 0.1. Instead of this, I would just write 0.09 and then keep repeating the 9. Okay. So when I'm saying it's an infinite decimal expansion, I mean that it's not all zeros after some point. It's going to have non-zero entries forever. Okay. So we've seen these things. And again, it's up to you to prove that there is a one-to-one correspondence between the set of infinite decimal expansions and the set of cuts. But it's a very trivial thing. Okay. So based on this, I want to figure out what is the size of this set R. And before doing that, I'm going to look at some particular subsets of R, and these are segments. So let's do a definition. I would define this. I would say, suppose that A and B are in R, and suppose that B is greater than or equal to A. Actually, I don't need this second assumption, but in any case, I'm going to put it there. So I define the segment from A to B to be the set of all real numbers such that this number X is between A and B, right? Super easy. And of course, I have the notation that you have all seen before. If I do something like this, if I don't use brackets, if I use parentheses, then it means that it doesn't include A and B itself. So it's like A less than X less than B. And then I can have things like AB and like AB and so on. These are all quite easy to define. Okay. And I'm too lazy to write it. So these are our definitions. I also want to define this thing. I want to say A, and I just put an infinity here. This is also going to be a set. This is an infinite segment. Actually, all of these segments are infinite, but this is a segment of infinite lengths. It's all X's in R such that X is bigger than A, but I don't have an upper bound. Right. And then similarly, I can define the closed segment, which includes A itself. I can also define minus infinity to A, which is the set of all X in R, such that X is less than A. Right. And again, I can define minus infinity to A and close that A, which means that I include A itself. Okay, so this is just a matter of notation, really. Now, what I want to prove is this. This is my theorem. I want to say that if I have 4 numbers, so if A, B, C, D are real numbers, and let's say A is less than B and C is less than D. Okay. Here are the things that I want to prove. First of all, I want to prove that it doesn't matter if you have a closed segment or an open segment or so on, all of them are the same size. Okay. So first of all, I want to prove that the segment AB has the same size as the segment AB and the same size as the segment where one side is closed, the other side is open, and so on. I don't care. Actually, there's only one more case. Oh, am I this lazy? So, okay, all of these are the same size, right? And then the other thing that I want to prove is that it doesn't matter which segment you're looking at, all the segments are generally the same size. So I'm going to prove that the segment AB from A to B is the same size as the segment from C to D. Okay. Now, the first part is actually quite easy. First of all, do you agree that all of these segments are infinite sets? Right, I hope I don't have to prove that. But actually, in order to show that, you have to have something more than intuition. Maybe I should prove that. I wasn't thinking about it. Okay. So for now, let's say I have a lemma that says all of these segments are infinite sets. I'll come back and prove that later. Okay, so lemma says that AB is infinite. And remember that here B is strictly bigger than A. Okay, because if A and B are the same, then this is just the empty set. Okay, so if I have an infinite set, we've had this previous theorem that says every infinite set has a countable subset. Right, so I can take a countable subset of AB. So basically what I want to do here is this. I want to say, consider the closed segment AB and the open segment AB. And suppose that I want to find a one-to-one correspondence between them, okay? So both of these are infinite, so I'm just going to consider a particular finite subset of the second one. Sorry, a particular countable subset of the second one. So let X subset of the open segment be countable. And we know such an X exists because we have proven before that every infinite set has a countable subset. Okay, so what is this X? This X is countable, so I can write its elements like this. I can label them X0, X1, X2, so on. Okay, so I'm going to have a function from the set. From which one to which one do you prefer me to do it? So let's do it like this. Let's do from the closed one to the open one. Okay, and I want this to be one-to-one and onto. So this is how I want to define f of x. Okay, or maybe instead of x, let me call it something else, f of t. So I want to take A, which is in my first set, but not in my second set, and I want to map it to x0. Okay, so it would be x0 if t is A. And then I want to map B to x1. So it would be x1 if t is B. And then for every other element here, I just want to shift it by 2. Okay, so if t is some xi, I'm going to map it to xi plus 2. So now I have mapped A to something, I have mapped B to something, I have mapped anything in X to something. Now I have the other elements that are not A, B, or in the set X. I'll map them to themselves. So T itself, otherwise. You can easily check that this is a one-to-one and onto function. Okay, so basically the idea here is that I have an infinite set. I'm adding 2 new elements. In order to find the one-to-one correspondence, I'm just going to find a finite subset, and then I'm going to shift the elements in that finite subset by 2. And for everything else, I'm just going to say map it to itself. Okay, and of course, I did this with the case where I had added 2 elements here. You can also do it with adding 1 element, so all of these things are the same. Okay, let's do the second part. Actually, instead of showing that all of these sets have the same size, I just show that all of them. So I just show that any segment from A to B has the same size as the segment from 0 to 1. Right? And this would prove that all of them are the same size. Okay, so I just need a function f that maps the segment from A to B to the segment from 0 to 1. Now the intuition here is very simple. Suppose that I have this segment from A to B. Okay, and let's say that I'm riding a car from A to B, and let's say I'm at some point here, X. Right? I just want to figure out what portion of this path have I already traversed, and then I'm going to map to that. So I'm going to say that take any number X and map it. Basically, well, I've traversed X minus A if I'm going to X, so map it to X minus A, and the whole length is B minus A over B minus A. Okay. So this is mapping all the numbers from A to B to numbers between 0 and 1. And again, you can easily check that it's 1 to 1 and 2. So these are all the same size. Okay. This lemma, why do we have that lemma? Why is it that A to B, if I look at this segment, it's infinite? So here's another theorem that I can use to prove that lemma. And the theorem is that rational numbers are dense in the set of reals. So this means that for every two real numbers, X and Y, for every X and Y that are real numbers, if X is strictly less than Y, then there exists some other number Z, but this one is going to be a rational number such that Z is between X and Y. Okay. Now, I'm kind of abusing the notation here again, right? Because here I'm saying that Z is a rational number, but here I'm using Z as a real number. So when I'm comparing it with other real numbers, when I'm writing Z is bigger than X, what do I mean here? I mean Z as a real number, but Z as a real number is just the cut at Z. Right, so this is the sets that contains the rational number Z and every smaller rational. Okay, why is this the case? So again, in human words, we say that rationals are dense in reals. Okay, so let's say that X and Y are two real values, right? So both of them are cuts. So both X and Y are cuts. Okay, so this means that X is a subset of Q and Y is also a subset of Q, right? But X is smaller than Y, which again, just following the definition means that X is a proper subset of Y, right? So what does this mean? This means that there is something in Y that is not in X. Let's call that Z. So there exists a Z in Q. Again, both X and Y are sets of rational numbers. So there exists an element in Q such that it's in Y, but it's not in X. Okay, this is exactly the Z that I want, right? So again, if you just look at the intuition here, it's like this. I have my set Q, and I have a cut here. So this cut is X. I have another cut. This is Y. Because they're not the same, there is some element of Q that is in Y, but not in X. Let's pick it somewhere here. Let's call it Z. Right? But now I can look at this Z, instead of an element of Q, I can just do a cut at Z. and I can look at it as an element of R. So I can just do this cut, right? And then Z is between X and Y. Fill out the details yourself. I'm not going to write all the details. Okay. Great. So why is this set infinite? Because B is bigger than A, so I can find a rational number between A and B. Let's call that rational number something, C0. And then I can find, I know that C0 is bigger than A, I can find another number between C0 and A. Let's call that C1. Then I find the number between C1 and A. Let's call that C2, and so on. So I can find infinitely many members of this segment. So the segment from A to B is infinite. Okay. Yeah, but these were pretty easy. I want to do something more interesting. Here's my next theorem. So if you look at all these segments that we were looking here at, these are segments of finite lengths, right? I mean, I haven't really defined lengths, but that's our intuition, right? The length of this segment is B minus A, which is finite. Whereas these are infinite length segments. So you might think that infinite length segments are bigger than finite length segments, but that's not the case. So actually, this is my next theorem. I say the segment from 1 to infinity, which means basically all the numbers, all the real numbers that are bigger than 1, has the same size as 0 to 1. And this also, of course, has the same size as minus infinity to minus 1. Okay. Now, I'm just going to do one of these. So let's say I have a function f from 0, 1, so this segment, to the segment containing all numbers bigger than 1. What do you suggest I put for this? So if I have some x here, what should I map it to? Yeah, just 1 over x. It's 1 to 1, it's on. Right? And if I want this for the segment from minus infinity to minus 1, I would just map it to minus 1 over x. Okay. So all these segments are the same size, which actually gives me my next theorem, which is this one. R itself, all of the real numbers, has the same size as a segment. And we've already seen that it doesn't matter which segment I put here. So every segment has the same size as all of R. Okay. Why is that the case? So I can just use this previous one, right? So I can write R as the union of several sets. I can take minus infinity to minus 1, union with, let's say, minus 1 to 1. I'm going to include both of them here. Union with 1 to infinity. Right. And I've already seen that I can map each of these into a segment, and it doesn't matter what my starting point and end point is. So I'm going to map this one in a 1-to-1 way to, let's say, 0 to a third. I'm going to map this one to 1/3 to 2/3. And I'm going to map this one to 2/3. Open 2/3 to 1. Right. And then this will give me a 1-to-1 correspondence between all the numbers in R and the segment from 0 to 1. Okay. Great. So you have just as many real numbers between 0 and 1 as you have real numbers overall. Okay. But exactly how big is this set? I mean, I just know that the set of real numbers is the same size as this segment, but how big is it? This is my next theorem. The set of real numbers has the same size as the power set of the set of natural numbers. So first of all, I've already seen that natural numbers and rational numbers have the same size. We've seen that rational numbers are countable. So based on this, I can already say that the power set of natural numbers has the same size as the power set of rational numbers, right? It's actually a quite easy deduction here. It's like I have a bijection from n to q. So whenever I'm given some subset of n, take every element and just apply the bijection, see what element of q you get, right? So every subset of n will also be mapped to a subset of q. Okay, great. But what do I know about R? I know that R is a subset of P of Q. Why is this? Because by definition, every element in R was a cut, and every cut was a subset of Q. So every element in R is a subset of Q. So R is a subset of P of Q, which basically means that the size of R is less than or equal to the size of P of Q, right? Just consider the identity function that maps every element in R to itself. It's going to be a one-to-one function from R to P of Q. Okay, and again, the size of P of Q was the same as the size of P of N, so the size of R is less than or equal to the size of the power set of the natural numbers. Okay, now I have to prove the other side. I have to find a one-to-one function from the set of subsets of natural numbers to the set of real numbers. Okay, now this function is exactly what you would expect it to be from the very beginning of this course. Whenever we were talking about subsets, we would just use a sequence of zeros and ones to show our subsets, right? So here's the thing. Suppose that I have some subset A of natural numbers. I'm just going to encode it as an infinite sequence of zeros and ones. Okay, so I'm going to look at every element of natural numbers, 0, 1, 2, 3, 4, so on. And I'm just going to ask, is 0 in my subset A? If it is, I put a 1. If it's not, I put a 0. And then I do the same thing for the next element. Is 1 in my subset? Suppose it's not. 2 is not. 3 is in the subset. 4 is not in the subset, and so on. This will give me an infinite sequence of zeros and ones, right? So here's the trick. Just put a 0 and a dot at the beginning, right? This is giving you a decimal expansion. It's an infinite decimal expansion. Okay. So we are mapping our subset to a member of R. And actually, this is between 0 and 1, too, which is really nice. We have to be careful about one thing again. And this is this nasty thing that we had here. Oh, I actually erased it. So basically, these sequences have to be infinite, right? Whereas if I have a finite subset, then this sequence becomes finite. Right. So for example, if my subset A is just 1 and 2, how am I encoding it? I'm doing 0 point, and then I say 0 is not there, 1 is there, 2 is there, and then all of the other ones are not there. But this was not an acceptable decimal expansion for a real number. So I have to do a corner case. I have to say, if this subset A is finite, take this last one here and just replace it. Do a 0 here and then put 9 all the way after that, right? So for finite sets, I'm going to have a slightly different notation. I mean, this number is the same as this number anyway, right? But I want to use this second notation. And for infinite sets, I just map normally. This is 1-to-1. So I have a 1-to-1 function. I don't know, let's call it G, from the set of subsets of natural numbers to actually, in this case, numbers between 0 and 1. And this is 1-to-1. Okay. Of course, I can also consider it as just being a function to R, and it's 1 to 1. So this means that the size of P of n is less than or equal to the size of R. Again, remember that I'm writing it as if these sizes have some meaning, but so far these sizes have no meaning for me. Whenever I say the size of some set is smaller than some other set, it just means I have a one-to-one function. Right? I have a one-to-one function from this one to this one. Okay. So I have a one-to-one function from R to P of n. I have a one-to-one function from P of n to R. What should I do? I should apply Schroeder-Bernstein. So by Schroeder-Bernstein, these two sets are the same size, which means that there is a bijection between them. Okay, great. So what have we seen so far? We started with finite sets, then we created infinite sets. We talked about the set of natural numbers. We saw a lot of countable sets. So like n times n is countable, q is countable. The set of finite sequences is countable. We saw a bunch of uncountable sets. And yeah, so at this point, we've also seen Schroeder-Bernstein, which basically says that if I have two sets and if A is smaller than B and B is smaller than A, then they're the same size, right? But then the next question is, if I give you two sets, can you always compare their size? So what is Schroeder-Bernstein telling you? It's just telling you that if you can find a one-to-one function from A to B, and you can also find a one-to-one function from B to A, I will give you a bijection between the two sets, right? Now, in some cases, I know that I can find a one-to-one function in only one direction. So for example, between natural numbers and real numbers, because of Cantor's theorem, I know that there is no bijection between n and P of n. So there is no bijection between n and R, right? But of course, there is a one-to-one function from n to R. Just map every number to itself. Okay. But then, well, would that always be the case? If I give you two different sets, is it always the case that there is either a one-to-one function from A to B or a one-to-one function from B to A? Now, you would be surprised, but apparently, based on the axioms that we have so far, we can neither prove this nor disprove it. So it's possible that we have a pair of sets that are not comparable with each other. It's also possible that we don't have any such pair. Based on our axioms so far, we cannot prove it either way. And this is where the axiom of choice comes in. So this is the last axiom we're going to talk about. This is ZFC10, and the C there is choice, of course. This is the axiom of choice. Now, I'm going to give you many different ways of saying the axiom of choice, and all of them are actually equivalent given the previous 9 axioms. So you can prove each one of these statements based on the other one. But as long as you agree that one of them is the axiom of choice, you have agreed to all of them. And then you have this nice property that every two sets are comparable. Well, actually, that's the first way I'm going to write the axiom of choice. So the first formulation that I'm going to give you, which is not exactly a standard formulation, but it's equivalent anyway, is that for every two sets A and B, either A is smaller than B or B is smaller than B. Okay. Or another way of saying this is that either I have a one-to-one function from A to B, or I have a one-to-one function from B to A. Okay. Great. So if I have this axiom, my life is much nicer because now I can really compare all the sets. And I don't have to prove that I can compare all the sets because it's an axiom. right? But here's another way of saying the same thing. And by the way, I'm going to prove that some of these things are equivalent if you have time, but I'm not going to prove that all of them are equivalent. And some of the equivalences are actually quite hard. They're above the level of this course. So here's another way to say the same thing, believe it or not, is this. Suppose that I have a relation. So let's say for any relation R. Now, what is a relation? A relation is basically a bunch of ordered pairs, right? So I have a relation R, and of course, every relation has a domain and a range. And we've talked about this before. So I want to say that for every relation R, there is a function f subset of R. Okay. So what does this mean to say that the function f is a subset of R? Well, every function is also a relation, and we said that the definition of function is that it doesn't map the same element to more than one element. Right. Well, so far this is trivial, right? Because for any relation R, I can just choose the empty set as my function, and it's a subset of R, right? So both R and F are sets of pairs. So, but what I want to say is this, for any relation R, there is a function F subset of R such that the domain of F is exactly the same as the domain of R. Okay. Now, if you think about this one, this is much more intuitive. So what this one is saying is, suppose I have some relation R. Oh, not that R, this R. So suppose I have some relation R. We defined what a relation is, right? We said that it's basically a subset of the Cartesian product of two sets, X times Y, okay? So let's say I have my set X here, and I have my set Y here, and I can think of this relation as a bipartite graph. So I can think that I have one vertex for every member of X, I have one vertex for every member of Y, and I have an edge between them if they are in relation, right? Again, I'm of course drawing a finite picture here, but this is not necessarily finite. X and Y can be any set. Okay. So this is not necessarily a function because, of course, I can have something like this. Right, so I can have the same element of X being in relation with several elements of Y. Right. And then what is the domain of X? The domain of X are all the elements in X that are mapped to at least something in Y, that are in relation with at least something in Y. So this part's the right side, this is the domain. Okay. So the axiom is saying that whenever you have a relation R, you can find a subset of R, which means a subset of edges in this case, because every edge is basically a pair, and that's exactly what a function and a relation are. So if I have this graph of the relation R, I can find a subgraph, meaning that I can take some of the edges, or I can find a subrelation, which is a function f, such that it has the exact same domain, but it's a function. What does that mean? This means that I have to go over every element here, every element of the domain of X, and if it's in relation with several elements in Y, I have to choose only one. So if there are several edges going out of this vertex, I'm going to say, forget about this one and only keep this one. This one already has only one, so I'm going to keep it. This one has 3 edges going out, so I'm going to remove 2 of them, right? This is a function which is a subset of my original range. All this axiom is saying is that for every relation, you can do this. You can find a function that is a subset. Okay. Again, in the finite case, it's so trivial. I'm just going to go over all the edges, pick one, right? But imagine that these are infinite or maybe uncountable huge sets with any possible size, and then how are you going to do it? Right? How are you going to choose an element of a really huge set? how are you going to choose an element of each huge set in a set of huge sets? This is something that, I mean, again, seems very intuitive, but it's really not. Okay. So I'm going to give you some other equivalent ways, but you see why this is called the axiom of choice, right? Because for every element in the domain of F, which is basically in this part here, in the right part, I have to choose what this element is mapped to. And it's called the axiom of choice because it says that there is a way to make a choice. Okay. So here's a third way. Let me see. Yeah, I can say that for every set A, there is a function. Let's call this one F as well. That maps subsets of A to elements of A, but non-empty subsets of A. This empty set is always a problem. So it takes a non-empty subset of A and maps it to an element of A such that for every B that is a subset of A and B is non-empty, I have that F of B is a member of B itself. Again, this is a very similar kind of situation. It's like I have a set A, I look at all the non-empty subsets of A. What I'm saying is that I have a way of choosing one element from each of these subsets. There is a function F that chooses one element F of B from every subset B. Okay. It's actually quite easy to show that 2 and 3 are equivalent. You can assume one of them prove the other one. Here's another way. This is also pretty easy. It says that suppose I have a bunch of disjoint sets. I can pick one element from each set. Okay, so this is how we would say it. We would say for every set A of non-empty sets. Okay, so A is a set of sets. Of course, I mean, every set is a set of sets, but A is a set and every element of A is also a set, but none of the elements of A is empty. Okay. For every set A of, actually, I should say non-empty disjoint sets, there is a set C and this C is a subset of union of A, such that for every element of A, for every A in A intersection with C has exactly one element. Okay. Now, again, this is quite a trivial thing. So this is what I want you to consider. Suppose that I have a bunch of sets. Again, of course, the example I'm going to give you is the finite case, but the infinite case is the important one. So let's say I have a bunch of disjoint sets. Okay. So let's say this is the set A1, A2, A3, A4, A5, A6. So my set A is the set of all these sets. So it contains A1, A2, A6. Okay. And each of these sets is non-empty, and each of them is disjoint. Each pair of them is disjoint. So there's no element that is in both of them. What the axiom is saying is that I can pick one element from each of them. So I can pick a set C, basically these red elements, such that there is exactly one element in every C and every set of my group. Okay, so the intersection of every AI and C is exactly. Okay. before I can give you the next way of saying the same thing, I have to define some simple stuff. So first of all, I have to define the concept of a chain. So I say a set C is a chain if for every two elements of C, one of them is a subset of the other. So for every X and Y in C, either X is a subset of Y or Y is a subset of X. Okay. Now, this might look weird to you, but just think of any natural number. Any natural number is a chain, right? Because what was, for example, the number 5? The number 5 was just the set 1, 2, 3, 4. Oh, they started with 0, right? This was how I defined 5, right? But let's take two of its elements. Let's take, for example, 2 and 3. What is 2? 2 is just 0, 1. What is 3? 3 is 0, 1, 2. So as you see, 2 is a subset of 3. Okay. So even though the definition might look very weird, it's like I have a set and I'm saying that for every two elements of this set, one of them is the subset of the other one. It's not that weird. We've seen many examples of chains. Okay. So the other thing is that I want to define a maximal element. So I say a maximal element of A, if A is a set, a maximal element of A is an element, let's call it M in A, such that for every other element, let's call it A prime, or just let's call it A in A. If A is not the same as M, then M is not a subset of A. Okay. So a maximal element is an element that is not a subset of any other element. For example, 4 is a maximal element of 5. 4 is an element of 5, and it's not a subset of any of the other elements. Okay. So finally, the fifth way of writing the axiom of choice is actually something that is known as Zorn's lemma. But this is also another way of just saying the axiom of choice. All of these are equivalent. And it says this. It says, let A be a set such that for every chain, B subset of A, we have the union of all the elements in B as a member of A. Then A has a maximal element. Okay. What does this mean? Well, A is a set of sets, right? So I'm saying that I have this set A, and in this set, I have a bunch of other sets. But I'm saying whenever I have a chain of sets, what does that mean? It's a bunch of sets such that I have one small set, then I have another one that includes it, then another one that includes that, and so on. Right? This is a chain. Right? Again, this is a finite chain, but of course, in my definition of chain, there was nothing about finiteness. It's just that if I look at any two elements of chain, one of them is a subset of the other. So I can have an infinite chain, I can have an uncountable chain, and so on. Actually, let me draw a nicer chain. So let's say this. Okay. So if I have a chain, what do I have? I have a bunch of sets that are getting bigger and bigger, right? But what is the union of everything in this chain? So union of B. I mean, if it has a biggest set, it's going to be that biggest set. but maybe I don't have a biggest set. So the union is basically the smallest set that contains all the sets in the chain, right? So I'm saying that if I have a set A and this set contains a chain, then it also contains just the union of this chain as one element. Okay. Again, and a good example of this is natural numbers. Of course, this is a finite example as well. I have a chain here, right? So I have like 0 is a subset of 1, it's a subset of 2, it's a subset of 3, it's a subset of 4, right? So this is a chain. It's a bunch of sets that are getting bigger and bigger, right? And whenever I have a chain like this, I mean, I can only take part of the chain. I can just take, let's say, 0, 1, 2, and 4, right? If I look at their union, in this case, the union of 0, 1, 2, and 4 is just 4. But that union is also a member of my set. 4 is also here. Okay, so that's the condition that I'm putting here. And I'm saying that whenever this condition holds, then I have a maximal element. And again, in this case, of course, I have a maximal element in this example. 4 is a maximal element. No other element is a superset of 4. Okay. So it turns out all of these are equivalent. And some of the equivalences are quite easy to prove. So you can easily go from 1 to 2 from, no, not from 1 to 2. You can easily go from 2 to 3, 3 to 4, and back to 2. So 2, 3, and 4 are actually quite easy to establish that they're equivalent. Let me do one of the hard ones. I can do 5 to 1. So Zorn's lemma, so this one that says for every two sets A and B, either A is smaller than B or B is smaller than A. Okay. So this is my assumption now. And again, remember, all 5 of these are just different ways of talking about the axiom of choice. And I promise you, I will not ask you in the exam to prove that any of these are equivalent. Okay. But I just want to show this. I want to show that assuming Zorn's lemma, assuming this lemma, we can compare any two sets. Assuming this lemma for any two sets, well, I'm already using A and B there. So let's say for any two sets C and D, either C has a one-to-one function to D, so the size of C is less than the size of D, or D has a one-to-one function to C. Okay, what should I do here? I should create a set of sets, and I should somehow have some chains there, right? So that I can talk about a maximal element. Here's what I'm going to do. I'm going to say my set A is going to be the set of all functions f such that the domain of f is a subset of C and the range of f is a subset of D. Okay. And also, well, I don't want all functions. So let's say all one-to-one functions. Okay. So what do I have here? Again, I have two sets C and D. I want to say that I have this set C here. I have this set D here. I want to say that either I have a one-to-one function from left to right or from right to left. I say, look at all the one-to-one functions that map some subset of C to some subset of D. Okay. Now, what does it mean for two functions? So if my A is the set of functions, what does it mean if I have a chain of functions? Remember, every function was basically a bunch of edges in this graph, right? With the condition that every vertex in C is going to have a degree of at most 1. It cannot have a degree of more than 1, but maybe there is a vertex in C that is not in my domain, so it has a degree of 0. And I don't care about the degrees of the vertices in D, they can have any degree, right? But now I'm saying I want to look at all one-to-one functions. So that means that I'm looking at functions where I'm looking at graphs where the degree of every vertex in C is at most 1, and the degree of every vertex in D is also at most 1. But I can have degree 0. Okay. Great. Now, what does it mean when one function is a subset of another one? You can easily see that it's the same as the graph of this function being a subgraph of the graph of the other one, right? So if I have a bunch of functions, so let's say I have two functions, this red edges are my first function, and let's say my second function has the red edges, but also has these green edges, right? So the second function is going to be a superset of the first function, and I can just create a chain of functions that are getting bigger and bigger. Okay, now, suppose that I have a chain of functions. So let's say B is a chain of functions. What is the union of B? It's just, again, in terms of the graph, it's just the union of all the edges, right? But each one of my functions was an extension of the previous ones. I mean, again, it's not countable, so I can't talk about previous ones. If I look at any two of my functions, one of them is an extension of the other one. So no two of my functions would ever disagree. So if I have a first function that mapping this one, let's call it alpha, to beta, then I cannot have another function in the same chain that maps alpha to somewhere else, right? Because then it would not be a subset anymore. It's no longer a chain. Okay, so whenever I have a chain of functions, I can take their union. And again, this was a chain of one-to-one functions. So its union is also a one-to-one function. So if I say that A is the set of all one-to-one functions whose domain is a subset of C and whose range is a subset of D, this is actually going to satisfy all the requirements of Zorn's lemma. For every chain B subset of A, the union of all the functions in B is also a function in A. Okay? Great. So now Zorn's lemma says that A has a maximal element, which means that I have a maximal one-to-one function in this set A. Okay, so there is a maximal function. Let's call it Fm because it's maximal in this set A. Okay. Here's what I claim. I claim that if I look at this maximal function, it either covers all of C or it covers all of D. Okay. And again, remember that it's a one-to-one function because I'm only working with one-to-one functions. So suppose that it doesn't. Suppose that I have a maximal function Fm, and there is an element in C that is not mapped to anything in D. And there is also an element in D that is not covered by anything from C. Well, I can just add this edge, and this is a bigger one-to-one function, right? So this would be a contradiction with maximality of Fm. So if I have a maximal function, it might be that it covers all of C, but D has a bunch of remaining vertices. Or it can be the opposite, that it covers all of D, but C has a bunch of remaining vertices. But in any case, I have a one-to-one function from one side to the other, right? So if this is a maximal one-to-one function and it covers all of C, but not all of D, great, I have a one-to-one function from C to D. Now, let's say it's the opposite. It's a maximal one-to-one function. It's covering all of D, but not all of C. It's covering all of D, so it's onto. So I can look at the inverse of this function, and that's a one-to-one function from D to C, right? So in any case, I'm either getting a one-to-one function from C to D or from D to C. So if I have Zorn's lemma, then I can also compare any two sets. But again, the really interesting thing here is that all 5 of these are actually equivalent. So If you have any one of them, you can prove the other.